Okay, so this is problem 1024. In this problem, we would like to find the moment of inertia about this weird shape that's bounded by the curves y squared equals b squared over ax and y equals b over a squared as x squared, where this point where the two curves meet is point AB. It seems like a pretty straightforward problem, I would say. However, we will try to find the moment of inertia first in order to see if we can actually solve it correctly. Now, we want to find the moment of inertia about the y-axis. And we already mentioned that when we're trying to find moments of inertia, it's very important to know, right, what is the axis you're trying to find it about, because that actually imposes some limitations on how we are going to solve this problem. Other than those small limitations, the steps are pretty much very similar to finding centroids, but your integral will be different. So the way we've been solving centroids in this class has been to first set a differential element. And of course, this is a two-dimensional shape, so my differential element will have a two-dimensional area dA. And of course, we would like to set that differential element at some arbitrary point xy. Now, our arbitrary point xy, remember, we typically pick that point on the curve that we are going to integrate over. And here we have two curves. So we have two selections on how to pick your points x and y, okay? One question, because we want to find the moment of inertia about the y-axis, should our element be horizontal or should it be vertical, or does it not matter? What do you think?
Should be vertical, right?
Okay, you're saying it should be vertical, right? What happens if I were to do horizontal? I would get the wrong answer, but do you know why I get the wrong answer?
Yes, you will have dy, which is along the y-axis, I believe, or
Parallel, right? Parallel to the
sorry,
y-axis.
yeah.
That's correct. So whenever we're trying to solve for the moment of inertia, remember the axis or the direction of your differentially small dimension. In this case, if it's horizontal, it'd be dy. It cannot be parallel to your axis. So that means that my element cannot be horizontal. So instead, I am going to try to pick an element that is vertical. So I'm going to set a differential element. Remember, this is a very, very, very thin element. So thin that we can actually look at it as a line. And this differential element will have this dimension, and we'll have this dimension that we can call dx. So we have a dimension of dx. What about this dimension? Is there any way we can express this length of the element? And just to make things easier, let's call this curve. Let's just call this curve my curve number 1. And let's call this curve my curve number 2. And the reason I'm doing that is so that this element is located, right, at my point y1 and at my point y2. So assuming that we know the location of y1 and we know the location of y2, can anybody tell me what this dimension would be, this length of the element? Remember, y1 is a coordinate, y2 is a coordinate. So what would this length be?
It's just y1 minus y2.
Yep. Good. So we set our differential element located at some arbitrary point xy. However, in this case, because we have two curves, I'm going to locate it at point xy1 or point xy2 because my element passes through both of those points. After setting our differential element dA, we need to find our x squiggly and y squiggly. Now you may realize that the reason I've been asking you to find both x squiggly and y squiggly is just so we can practice relating the centroid of the element to our different coordinates. However, because we're finding the moment of inertia about the y-axis, you can see that really what's important is to find our x squiggly, because the moment of inertia about the y-axis will be the integral of x squiggly squared y squared. We can still find y squiggly, but just keep in mind that that is just for practice, but we do need to find x squiggly. And if you haven't reviewed centroids yet, just as a reminder, x squiggly, actually x tilde, but we call it x squiggly, represents the x coordinate of the centroid of this differential element. This differential element is so thin that we can treat it as a rectangle. Therefore, its centroid will be located at its center. Yeah, that's what we say when we say x squiggly, that is what we mean, okay? The center, the coordinate to the centroid of this element. Now, this element is actually located at a position x, y1 here, and in between x, y1 and then x, y2. So when we're trying to find the centroid x squiggly of that element, what would that coordinate be with relationship to your x coordinate? So if these 2 points are both at the same x coordinate, what's the coordinate of the centroid, which lies right here?
It'll just be x.
Just x, okay. So we get x squiggly equals x. We don't really need y squiggly, but just as a review, let's talk about that quickly. Y squiggly would be the y coordinate of this point. Notice that this point is actually the average of y1 and y2. So y squiggly would be just 1/2 y1 plus y2. We don't really need it here, but it's always good to review. Just make sure we understand how this differential element relates to the curve as a whole, the shape as a whole. All right, we found our differential element. After finding our differential element, we can express our area, which we're going to call dA. We can express this area dA in terms of our differential dimension. In this case, notice that our differential dimension is dx. Therefore, we are going to express dA in terms of dx. In other words, we want to relate that area dA to the dimension dx. Now, I'm going to try to draw the element here just so that we can see it a little bit better. We have an element. This is my point x, y2, and the top is my point x, y1. From the element, we can see that this length, this base is dx. So this base has dimensions of dx. And we can see that this height has dimensions of y1 minus y2. So that is our differential element and its dimensions. So if I were to ask you to express the area of that element, right? The area of that element in terms of these dimensions, then what is the area? Oh, I wrote dA here in terms of dx. Then what is the area of the element? So if I ask you to calculate dA based on the dimensions that are given here, what is dA?
It'll just be y1 minus y2 times dx.
That's correct. Ray, I realized that you were kind of waiting to see if someone else would answer. That's very generous of you, but online students rarely participate. So I'm okay with you continuing to answer the questions.
I do have a question though. On your y squiggly, why is that a half y1 plus y2? Why is that not a half y1 minus y2?
Because this is the average coordinate of this point, right? So y1, when you look at y1 in terms of this Cartesian plane, y1 represents the distance between the x-axis and this point, right?
Yeah.
Okay, so I'm just going to draw it here. This is y1. And then y2 represents the distance between the x-axis and the bottom point, right?
Okay.
So what we're looking for is the distance between the x-axis and the point that lies in between those 2 points. And this distance is just the average of these 2 numbers. The average of 2 numbers is the sum of the numbers divided by 2.
Okay.
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 But good. We get that our dA, our area, is y1 minus y2 times dx. do these values y1 and y2 change? If I were to move my differential element from here to here, would these y values change or are they constant?
They're constant.
Really? Let's see.
I'm sorry. Now your x changes, so it's not constant.
Okay, so if I were to draw another element here, notice that y2 is actually higher, is a different number, and y1 is also a different number, right?
Okay.
What that means is that because these two are not constant, they change, we need to express them in terms of our differential dimension. So here our differential dimension is dx, therefore y1 and y2 need to be expressed in terms of that dx. And that's what we're going to do. y1 and y2 need to be expressed in terms of dx. So how do we do that? We do that by using the equations given to us, right? By using the curves which themselves relate y to x. So I'm going to write down the equations here just as a bit of a refresher. We know, and this is given to us, right? We know that my curve number 1, y1 squared, is equal to b squared over ax. And we know that y2, which is my second curve, is equal to b over a squared x squared. So given this information, we actually know what the relationship is between our y curves and our x curves. In this case, if we look at y1, since we have y1 squared equals b squared over a times x, we can always say that y1 is equal to the square root of b squared over a times x. And then y2 is equal to b over a squared times x squared. So we can write them down and express our area dA in terms of only our x variable. B and A, remember, they're not variables, they're constants. They're the point where the two curves meet. So they're just constant points. In this case, we get dA is equal to y1, which is the square root of b squared over a times x, minus y2, which is b over a squared times x squared, times dx. And now, the fourth and the final and the most exciting step for us is to integrate. Notice that the hardest part of this problem is actually setting up the problem, right? We want to make sure that we set up our x squigglies, y squigglies, and our dAs correctly, because if we fail at any of these three steps, we're not going to get the right answer in the end. But once we do have that our integral set up, then really all we have to do now is to integrate and solve this problem. The moment of inertia about the y-axis, which is what we're trying to find, is equal to the integral of x squiggly squared dA. From step number 2, we find that x squiggly equals x. Therefore, this is just the integral of x squared dA. From step number 3, we find that dA equals square root of b squared over ax minus b over a squared x squared. So we can write this down, right, as square root of b squared over a times x minus b over a squared x squared. Dx. So at this point, we're just replacing numbers, right? Plugging numbers in and solving. Now, there is one final detail that I think we need to keep in mind before we try to solve a problem like this, and that is our limits of integration. Because we are integrating over the x-axis, over the x direction, we want to make sure that our limits include all of the x terms in these two curves. That means we got to go from the leftmost point to the rightmost point. So what's the leftmost point in this equation?
Be 0.
0. So we're going to integrate from 0. And on the right, we see that this is point AB. So we're integrating from 0 to A. So we're integrating this equation from 0 to A. So let's go ahead and solve this equation. The sum of an integral is equal to the integral of the sums and vice versa. So remember, we can just integrate this term individually and then this term individually. So x squared multiplied by this and then x squared multiplied by that. But anyway, these should not be too hard to solve. We get that the moment of inertia about the y-axis equals the integral from 0 to a. If I multiply x squared times square root of x, remember that square root of x is just x to the power of 1/2. So x squared times x to the power of 1/2 should be x to the power of 5/2. Okay, so I can write it down. This will be the square root, and just leave this alone, of b squared over a. This is a constant, times x to the 5/2. Okay, minus multiply x squared by x squared. That's just x to the power of 4 dx. And finally, we just integrate, right? I'm going to take out my constant, b squared over a square root. And this will be x to the 5/2. So the integral of x to the 5/2 should be 2/7, right? X to the 7/2. And here we have a constant, b over a squared. And we get the integral of x to the power of 4 is 1/5 x to the power of 5. And all of this, remember, is evaluated from 0 to a. At this point, I don't really think we need to explain much more, but let's just go ahead and solve it completely so that we can compare our answers to each other and make sure that we have the right answer. So we get that the moment of inertia about the y-axis will be equal to what? Since this is a square root, I'm just going to take the square root of these two terms. The square root of b squared is just b. The square root of a is just a to the 1/2. We multiply this by 2/7. I'm going to put my numerical coefficients to the left. So times 2 divided by 7. And then this is times a to the 7/2. Okay. And here I get, I'm going to move my numerical coefficients to the left. So 1/5 b over a squared times a to the power of 5. A to the 7/2 divided by a to the 1/2 is a to the 6/2. And a to the 6/2 is just a to the power of 3. So this gives me 2/7 a to the power of 3 times b minus 1/5 a to the power of 5 minus a to the power over a to the power of 2 is a to the power of 3 times b. And finally, we get 2/7, right, minus 1/5. So 2/7 minus 1/5, I can factor out the a to the power of 3 times b. And if I want to subtract two numbers, I can just find a common denominator. So if I multiply the first term by 5/5, I get 10/35. If I multiply a second term times 7/7, I get 7/35. And this finally gives me 3/35 times a to the power of 3 times b. And that is the moment of inertia about the y-axis for this figure. So if you look at the problem firsthand from the book, it seems like it's going to be complicated, but notice that as long as you know how to set your differential element, find the x squiggly, y squiggly coordinates of the centroid of the element, express the a in terms of your differential dimension, in this case dx, then integrating really isn't that complicated, okay? So any questions with this problem? All right, if there are no, go ahead, sorry, didn't hear you there. Go ahead.
How did you get x squared times the square root of x is 5/2?
Yeah.
Maybe I missed it.
Yeah, no problem. Just to confirm, are you saying how do I go from here to here?
Yes.
Okay, cool. Let me just write it down here. we have x squared, right? That's one term. And then we are multiplying it by the square root of x. So you know that the square root of a term is just the element, is just the term raised to the power of 1/2, right? And
Yes.
when we multiply two terms that have exponents and they're the same term, we are essentially adding the two exponents, right? So this is x to the power of 2 plus 1/2. Now we have different denominators, so we need to find a common denominator. So I can find a common denominator by multiplying this number by 2 over 2. So 2 times 2 is 4 divided by 2 plus 1 over 2. And then 4 over 2 plus 1 over 2 is just 5 over 2. And I get x to the power of 5/2.
Okay, got it.
Okay. Any other questions? All right. If there are no more other questions, I hope this review session was helpful. Hopefully this is a homework problem, so we'll definitely help you with your homework, but hopefully this will help you kind of like solve the other problems with the homework.
I did have a really good question.
Mhm.
You said, I think in the first class on Monday or Tuesday, I'm sorry, you said that we can't, how should I say this? When we're using, let me go back to my notes. Like differential dimensions can't be parallel to its axis.
Mhm.
And then you said, but there is a way that we can do it. Did you mention this in this video that you released?
We covered it in today's class, a video that I just uploaded like a few hours ago. So you'll
Okay.
see it in that video. I'm
Okay.
gonna post an announcement on D2O with saying that I uploaded the video. So yeah, we already talked about it. So just to do a quick recap, it's through a theorem called the parallel axis theorem, and we're gonna learn about that in the video that I uploaded a few hours ago.
Okay.
All right. If there are no more questions, then yeah, good luck with your homework, and email me if you need any help with your homework.